Hello everyone, thanks for joining. In today's lab, we're going to be utilizing the BL-01. Now the BL-02 and the PT-201 utilize the same level 1 curriculum that's included in the workbook. I chose the BL-01 because of its lightweight and its small footprint. But as I said, all three of these units utilize the same curriculum, so no matter which one you're on today, you can follow along. In Lab 5, we're going to be working with a basic math and logic program. In this lab, we'll be working in Sedona Application Editor. We'll be selecting the required components to make our program work. We'll be linking the components and the slots together, comparing the program with a sequence of operation, and then we'll create our own unit heater program. A little background on Sedona Application Editor, also known as SAE tool. And with that, we can connect to our controller. First step we'll do is connect in the web browser. And we can see we've loaded up the controller in the web browser. We can see some of our inputs are working. And now we'll open Sedona Application Editor. So with Sedona Application Editor open, we'll have to make a connection to the controller. So you can do that through this quick connect button here, open connection, or file, open connection. Type in your host and port number, username and password, and now we're in the SAE tool. So if you remember from previous labs, we have our different panes. We have the navigation pane, the kits pane, the wire sheet, and the properties pane. In lesson 4, we reviewed some of the kits that are included with the BAS Control 22. And so here's some of the I/O points that we'll be utilizing. So in our wire sheet, we're going to open the Sheets folder. If you're following along, this is the program that we created in the last lesson. We'll be utilizing a lot of the same components, but we need to delete the links, and we need to delete the component one-shot and FTOC. So you can delete each link by clicking it and clicking the delete icon up here, or you can right click and delete, or you can try to select multiple by holding the control button and then hitting the delete, or you can highlight and delete. So there's multiple ways to work in wiresheet. So we've deleted the two components that aren't needed, as well as all the links. Now we'll be dragging these components onto the wire sheet, the AND2, the NOT, the ASW, which is an analog value toggle switch, and the high steer component. In our kits pane, we'll open the logic kit and we'll drag AND2 over. We'll also use the NOT component, the ASW, the analog switch. We'll minimize the logic kit. We'll open the function kit and we'll grab our hysteresis here. We won't need the delay on for now, so we can delete that. And there we've kind of organized the components into the way that we'll be utilizing them. A quick note, in the object-oriented programming world, the logic always flows from left to right, inputs on the left, virtual components in the middle, and outputs on the right. We aren't using the 4 inputs that are on the bottom, but they're not harming anything, so we can either delete them or just leave them on the wire sheet. If there's no link to them, then they're not doing anything. Let's take a closer look at some of the components that we're using. So the AND2 and the NOT objects. The NOT is an object that will reverse the Boolean input. And the AND component, also sometimes called an AND gate. The AND component or object adds 2 inputs. So in the example here, if A is false and B is false, then the output is false. Here we can see the ASW component and the high steer component. So the ASW is determined, the output selection is determined by the S1 state. So on the left example, you can see S1 is false, and that would mean the output on the top is equal to input 1. If S1 is true, as on the right, then the output is equal to in2, 20. The high steer component is starting to get into more of the complex components that we'll need for these HVAC programs. It deals with the rising edge and falling edge and is pretty configurable. If you'd like to learn more about components, there's a lot of great resources out there. In the SAE tool, the help section has a lot of good details and information. And then you can also look at the Sedona Open Reference Manual, and that has a lot of good knowledge as well. So we've dragged our components onto the wire sheet, and now there's two important tasks that we need to do in order to complete the program. We need to link the output slots to the correct input slots, and then we need to configure those slots with the desired values. So binary input out is going to the in. Binary input 2 out is going to this into. So now we have, if this and this are AND function, then the out will feed the in of not and also it'll feed to binary output input. And so you can see it doesn't look that neat. If I drag this down, it makes the connection. It's making the connection. When I drag this up, it just doesn't show the line complete. So I like to see the line complete. So we'll reorganize it a little bit, make it a little neater. Now the not out is going to binary output 2 input. So universal input 1, if you remember in our web browser, is the zone temperature. We're going to utilize the out Fahrenheit, and that will feed the high steer component in. So you can see 69.92, 69.91 or 92. I'm going to reorganize this to bring universal input 2 up here. Now universal input 2 is the supply air temperature. So if we go back to our wire sheet, and so we want the out Fahrenheit to feed the rising edge and also the falling edge. So again, I didn't like how the lines were orienting. If you look like that, if I move it here, it looks like these lines are connected. So if I bring it down, it kind of showcases a little bit better. In the programming world, I like to see everything spelled out and no lines connecting like that if they're not actually connected. So on our high steer component, the out is going to feed binary output 3 input. And we're not using binary input 3, so I can delete that one, move this up a little, just try to make it a little bit neater. Now universal input number 3, on our web browser, we're seeing that's the local zone temperature set point. Now 305 degrees, you might have some issues. Universal input 3 is very sensitive, so if I bring the dial down, and let me turn auto refresh on here, you can see it drops pretty dramatically. So let's bring it to something a little more realistic. 55 degrees. Okay, we'll deal with that. It's pretty cold. So back to our wire sheet. Universal input 3, the out Fahrenheit is going to reset in, and then the reset out is going to ASW into. A little more reorganizing. And I'm on a fairly small screen. Ideally, you have an external monitor, you hook it up in the field, and you can have this bigger screen, or you're doing the programming in the office and then transferring it onto the controller. So ASW, the out is going to go to analog input. Sorry, the ASW out is going to analog output 1 input Fahrenheit. So you can see nothing's translating to analog output 1 because we need to complete the linking. So we'll scroll down a little. Web component 2, F value is going to feed the input of ASW. So if you remember, I deleted binary input 3. I thought we didn't need it, but we do need it. So we'll drag that component back on. We'll go to the kits pane. We'll open contemporary controls, BAS22, IO. We'll drag BI3 down to the bottom here. As you remember, inputs to the left. And now the out of binary input 3 is going to feed S1 of ASW. So again, I don't love how this looks. Okay, so there I can see everything's flowing properly. So now we have all our components linked. If I scroll up, you can see the rest of it. If I scroll down, you can see the complete. And so it doesn't fit all on my screen, but I can scroll up and down and see everything. Now that we've linked our components and we have a potential program, we think we have a program, I want to talk about sequence of operation, SOO. There's two important questions that a programmer must answer when dealing with an SOO. What exactly do I need to do, and how specifically am I going to do this? Exactly and specifically are very important because you may have heard the term, the devil's in the details. If you mess up those little tiny details, they can be huge the further and further or the more complex it goes. And so you can see when I was working on the wire sheet, I really wanted those links to be spelled out perfect visually for me to make sure that nothing was linking improperly. So let's talk about a very basic SOO. We have to heat a room to 70 degrees, so the set point shall be fixed at 70. If the room temperature, which we'll measure as an analog input, 1, if that drops below 69, it'll turn on digital output 1. When the room temperature rises above 71, it'll turn digital output 1 off. And so the digital output is an electric heater, the input is a temperature sensor, and the logic, how we're completing this all, is either a thermostat or a controller. So even with this very simple SOO, we need quite a bit of detail in order to make this work. Below is a more complex SOO. So you can see when we get into dual modes, occupied state versus unoccupied state, things start to pick up. Things start to get a little more complex. So on the left here is an actual AHU, air handler unit, sequence of operation that you might find on a print or an engineer spec. Again, we're following that left to right flow. So the input's on the left, the logic is in the middle, and the output's on the right. SOOs are written this way as well. Hopefully this gives you a very brief overview of a sequence of operation. There's a lot of training and a lot more detail that goes into it, and we could spend hours just on the SOO, but I wanted to give you a brief overview before we jump back into our program. And so back to our math and logic program. We talked about the SOO, and these are usually given from an equipment manufacturer. So if you order an air handler, sometimes it'll come with an SOO that's required for this air handler, or it'll be written in the engineering specifications, whether this is on the blueprint or in a specification guidebook. Okay, so we've linked our components, and now we can start to test our sequence of operation. And so we have binary input 1. Hopefully you can see this. We have binary input 1 and binary input 2. They're both in the down position, which we'll say is in the off position. So on our wire sheet, we can see binary input 1 is false. If I click that, it becomes true. But we're using the AND logic, so both these inputs must be true. If I click binary input 2, that creates true. If we follow the link, it goes to the not in, which is true. So the out is not true, it's false. Binary output 2 is false. And if you can see down here, the lights, binary output 2 is off right now because it's false. Binary output number 1 is true. If I click one of these off, you see the green light turned off. That's binary output 1, because now that input is false. That's feeding off of the AND. So if both of these are true, if 1 and 2 are true, then it'll turn binary output 1 on, energizing the light, turning it on, the green light would come on. So it came on. If I turn one of them off, shuts off, the yellow light, which is binary output 2, is energized because that's using the not function. If I turn them both off again, it's still using that not function. Binary output 2 is on, it's energized. If I turn both of these to true, then that turns off and binary output number 1 turns on. So we see that function is working correctly. In the HVAC industry, this could be motors turning on and off. It could be fans turning on and off. There's a lot of different applications that this could be used for. It could be used for security doors. If this door is open, this door can't open, such as you'll see in a prison. There's a lot of different functions that you could do with this. So hopefully we're starting to see this and not function come into play. For number 2, we can see if universal input 1, which is our temperature, this is actual room temperature. If this rises above universal input 2, set point, then BL-03 will be energized. So BL-03 is the red light down here, and let's say that represents the HVAC heater. So when this heater is activated, it'll turn on, start heating the place. And so if we look at our wire sheet, we have universal input 1, which is showing 71 degrees. Universal input 2, which is the dial, is currently showing 83 degrees. So BL-03, binary output 3, is currently false or off. So now let's bring this temperature down. It's getting colder at night. We can see it dropping, and there it just clicked on. The heater just turned on. So the temperature got to 62 degrees. The heater kicked on. So now the heater starts rising. 64, 70, and there we hit 73 degrees. Binary output 3 turned off. The red light turned off. In my example, that's representing the heater. The heater turned off. So we can see that function's working. And now the last function we can look at is number 3 here. When binary input 3 is off, analog output 1 shall have a fixed 5-volt output. When binary input 3 is on, meaning we hold the switch in, analog output 1 will vary from 0 to 10 volts based on the position of universal input 3. This one will be a little bit trickier, but we can see here binary input 3. So binary input 3 and universal input 3 are working with the voltmeter. If binary input 3 is off, the voltmeter reads 5.08 in this case. If we click it, it's going to be based upon where universal input 3 is, which will show the voltmeter. So if I start to mess with this dial, we can see the voltmeters changing. And again, this dial is very sensitive. But essentially, we can see that it's working correctly. If this switch is not held, and this could be a heating, a vent, a motor, a cooling application, it varies in many different circumstances. Again, I related back to security doors. This could be this door is open, this remains at 5 volts. If this door closes, then it bases it on how strong the pressure is, right? There's so many variables that we could program, but we can see that it's working. If this is off, then this stays at the 5.08 volts or whatever it's set for. And when this turns on, it varies from 0 to 10 based on the position of universal input 3. So you can see it changing there. This dial is very sensitive, so it's hard to get from 0 to 10. So we can see our program works. Again, this was a Semi-complex program. The units that we used were kind of based on an HVAC application, but this could be used for a lot of different things. So now let's work on another program. Let's relink the components and meet the following sequence of operation. We're going to be dealing with the unit heater, UH1. When the occupancy switch is on and the space temperature drops below the space set point, then the fan shall be enabled, and after a 5-second delay, the heating value shall be opened to 80% or 8 volts. So let's start with binary input 1. The output is going to feed and input 1. Now, universal input 2, the out Fahrenheit is going to the high steer in. The high steer out is going to the not in. And the not out is going to the and in. That's funny how it did that. There we go. That looks a little cleaner. The out from the and will feed binary output in, as well as the delay on. So let's bring that up here. So the out from and to will also feed the delay on input. The delay on out will feed the ASW S1. The out of ASW feeds analog output 1 in. And the delay time we need to link to web component 2. So our FAT value is going to feed into the delay time. Okay, so we can see our flow is starting to make a little sense here. Now we have a couple more things to link. Universal input 3 is going to the reset, so the out F is going to the reset in, and then the reset out is going to the high steer rising edge. Try to make this a little neater. So as I said, the out is going to the rising edge and the falling edge. Ooh, I really don't like how that looks. What a mess. Okay, that looks a little neater. So there we can start to see our flow. So if we look back, when the occupancy switch, binary input 1, if that's on, then universal input 2, okay, this temperature, 76.41, if that drops below the space point, set point of universal input 3, we're feeding into high steer. So you can see the universal input 2, the out feeds into in. Universal input 3 goes to reset, and then it hits the rising edge and fall. The output is true right now because this is below this, right? 74.35 is below 76. If I adjust universal input 3, you can see 78 goes above 76. So the not becomes, the in is false, so the out becomes true, right? That's our not function. That creates the and, which is feeding into in2. Binary input 1 right now is on. If I turn that off, you can see the and function. Both of these have to be true, and so binary output 1, the green light here, is off. If I turn this back on, the light turns on green. Now one thing to note is if something's not working, sometimes you have to enable the component. So you can right click, action, enable. I had some trouble because it was disabled, and you can see the component's not working, when I enable it, now it's working. Okay, so our web component 3 is our delay time. And if we open our web component, we can adjust that from, I think we specified 2 seconds to a maximum of 10. So we have it for 8 seconds. Let's go to 3 seconds. We'll submit that. In our wire sheet, we can see web component, the F value dropped to 3. We changed that to 3 seconds. So our delay time is 3 seconds here. And so as I adjust this universal input 3, which we're calling the space set point, so if this set point drops below and it turns this heater on or off, if I adjust the dial, count for 3 seconds, the light turns off, or the fan turns off, or the heater turns off. So our unit heater is functioning as our sequence of operation is programmed. Take you through one last time. This is an occupancy sensor or switch. So someone's in the building right now. If I turn that off, now it doesn't matter if our space temperature, universal input 2, drops below or above the set point, universal input 3, because nothing's on, right? The occupancy switch is off. So binary input 1 you can see is false on our wire sheet, it's off. If we're using the AND function, both the inputs need to be the same. So right now they're both false. That creates, this is false. So binary output 1, the heater, is currently off. The green light's not on. It doesn't matter if I turn these dials, the set points, if it goes to 100 degrees, whatever the set point is set for and what we've programmed, it won't matter because the occupancy switch is off. If I turn this on, the heater turned on. Now, these inputs, universal input 1 and 2, which are our set points, will matter because the occupancy switch is on. And if we're looking at our logic, our AND 2, they're both true. So if we follow the flow, it comes from NOT, which comes from high steer, which comes from universal input 2 and 3. So if I adjust universal input 2 and I bring it to 120 degrees, the heater turned off. Universal input 3 is a space set point. And so we're at 55 degrees or 56 degrees. That's what our set point is. Now the temperature, let's say it starts to drop. And I'm adjusting universal input 2. And it's slowly dropping, 98, 84, 72. The temperature is really dropping now. 59, 55. And there's a 3-second delay, and it turned on the heater. Binary output number 1. For a beginner, this is a very complex sequence of operation. Out in the field, if you've been doing this for a couple years, it's probably pretty basic. To wrap up, hopefully this lesson was very helpful. We did a basic math and logic program, we utilized the sequence of operation, and we configured it in the wire sheet, we linked the components, and we saw how things communicated to each other. This application can be used in the HVAC, security, IT, whatever industry you're in and you're using this logic and this programming, it's very applicable to a lot of different industries. You can see the next lesson, Lab 6, we get into a basic PID loop program. So hopefully you learned a lot today. Thanks for watching. Join me for the next lab.